Hey, I'm Ophir, and I've been doing language modeling research for 8 years. In this video, I'm going to teach you how transformer language models work by building 5 increasingly complex language models. I think it's a really intuitive way to understand how the current state-of-the-art transformer language models work. The only prerequisite knowledge that I'm going to assume is that you know how to multiply 2 matrices, and that's it. If you know how to do that, you'll understand this whole thing. So yeah, let's dive right in. So, what is language modeling? We have a sequence of words like Ophir is teaching, and we are trying to predict the next word. That's a language model, right? What word goes here? And in order to do that, the kind of first step is to get a training set of examples. And that's pretty easy. You can just crawl the web, get a bunch of text, and then concatenate it all into one large string. And then you have this big training set to train on. And in order to make this training set, you just take your string, that's the input, and then your target outputs are the words that appear in the future. So when we input Ophir into our language model, we are going to expect it to output the word is. When we input is, we're going to expect it to output teaching, and so on. So that's your training set.
Now, is
Yes.
the training set one question? Is it Ophir is, and kind of these growing subsets, or do you sometimes start mid-sentence too and just start with is? Like, do you keep all possible subsets, or just these kind of growing from the beginning of the sentence?
Yeah, well, we'll talk. That's a good question. We'll talk about that later.
Okay.
But we have this really long training set, and we're now going to build a really basic language model. And actually, in this language model, we're only going to look one word back. Okay? So it's going to be a super basic language model, and it's going to get one word and try to predict the next word. And then so it's going to take that word and try to predict the next word, and so on and so forth. And here's how we do it. So we're getting a word, Ophir, and now we want to predict the next word. So we're going to represent our input words by a vector. So we're going to have, let's say, 1,000 numbers, 1,000 floats to represent each word, to represent each input word. So fear is going to have a specific vector. And is going to have a specific vector, and Alex is going to have a specific vector, and dog is going to have a specific vector. And we're going to take the vector for Ophir, and it's a vector of size 1,000. And now the way a language model's output looks is that it doesn't say, okay, the current input word is Ophir, I think the next word is. It doesn't make those kinds of like concrete or like discrete outputs. What it does is it gives us an output distribution. So it's like, okay, the current input word is Ophir. I think that the next word is with like 10% probability. I think that the next word is was with like 5% probability. I think that the next word is will with 2% probability, right? So that's what a language model does. It doesn't return a specific word. It takes our entire vocabulary and it assigns a probability distribution, a chance to each word in our vocabulary. So let's talk about, I guess, vocabulary. We should have talked about it before, but let's talk about it now. So when we do language modeling, we have to pick a vocabulary, right? It's a really deep subject, and it's not super critical. So we're just going to assume that our vocabulary for now is just the 50,000 most common words in the English language. Okay? That's a vocabulary. And then to make sure that none of our words are out of vocabulary, we'll also add in all the characters in the Latin alphabet. So our vocabulary is the top 50,000 most popular words in the in English, and then all the letters in the alphabet, and that would let us express any string of characters in the English alphabet we can express with this vocabulary. Okay, so that's our vocabulary. So for each input word, we have this vector representation, right? And we have one for Ophir. That's the first step in this very basic model that we're building. And now I need to build a model that will return a distribution, which represents my model's prediction over the next word. And here's how we're going to do it. We're going to have a matrix, and it's going to be of size. So we said that this vector for Ophir, it's of size 1,000. It's 1,000 floats, right? So I'm going to have a matrix here, and you're going to have to correct me if I get any of the dimensions wrong. But I'm going to have a matrix here, and it's going to be of size 1,000 times 50,000, right? Mm-hmm. So our vocabulary is of size 50,000. I know I said 50,000 plus, the letters in the Latin alphabet, but let's just assume it's 50,000. So, right? So I told you that what I wanted to give you was a distribution over the next word. So this is how we're going to do it. We have our input word Ophir. Then we have this matrix that's of size 1,000 times 50,000. And we're just going to we're going to multiply. That means that it's going to result in this, for this input, it's going to result in a vector of size 50,000, right? So this is 50,000. But this vector is going to be a vector of floats. But I promised you that I would return a distribution. And so what we're going to do here, we're going to now just softmax it. And so that's going to return a vector of 50,000 floats, but this time they're all going to be between 0 and 1, and their sum is going to sum to 1, which means that this is going to be a distribution. This vector right here is a distribution. And so that's our super basic language model. It gets in a word, and it returns a distribution over the next word. Hey, this is Ophir from the future, and I'm editing this video now, and I notice that I'm going to use the word softmax without ever explaining what the softmax layer does. So I'm quickly going to explain what softmax is, and then we'll get right back into the video. Okay, so we have this model right now where I inputted the word Ophir, and I'm trying to predict the next word. And so the first thing I do is I get the word embedding for the word Ophir, and that's a vector of 1,000 floats. And then I multiply it by this matrix that has 50,000 word vectors, each of size 1,000. I get this vector of size 50,000, and we call this vector the logits. And then these are just numbers, but we want to return a distribution. And so now we're going to softmax the logits to get an output distribution representing the model's belief about the next word, right? It's going to tell us what probability it assigns to each word in our vocabulary. And so I'm going to explain what the softmax layer does, but before I explain what the softmax layer does, I'm going to briefly explain what the logits are. So we have this input word Ophir, and then this vector, this matrix here of size 50,000, it's actually 50,000 word embeddings for each word. So the first column here might be the embedding for the word cat. The second column might be an embedding, right? It's all, these columns are each of size 1,000. So the second one might be the word embedding for the word dog. The third one might be the word embedding for the word is, and so on. So each column here is a word embedding. And so the logits, what happens when we multiply this vector by this matrix is that every number that we get here is going to be the result of multiplying Ophir by one of the representations in this output, in this matrix here, which is sometimes called the output embedding. So the first logit here, the first number here, is going to be the product of cat times Ophir, and that's going to represent the model's belief that the next word is going to be cat, and that might be, let's say, 50, right? And then the second number in this vector is going to be dog times Ophir, so that's going to represent the model's belief that the next word is dog, so that's going to be 49, let's say. And then the next one is going to be is times Ophir, so that's going to represent the model's belief that the next word is, and if the model has already done a bit of training, we expect that number to be high because that's a pretty likely output, and so that might be like, I don't know, 800, right? And so on. So every word is going to have a logit attached to it. And these logits are going to correlate with how strongly the model believes that that word is the next word. But then, of course, we can't output logits because we need to output a probability distribution. And so the last thing that we need to do in this network is to normalize these logits. And that's what the softmax does. So the easy way to normalize would be to just take each logit. So this is the ith output in the kind of naive normalization, to take the ith logit and to just divide it by the sum of all the logits. But that wouldn't work here because some of these logits are going to be negative. I'm not really going to get into what the meaning of that is, but some of them are negative, and so we can't use the simple naive normalization function. And so we use a slightly more complex one that can handle negative numbers, and it's called softmax. And it's basically this function, just that we exponentiate everything. So it's going to be e to the power of the ith logit divided by the sum of e to the power of all the other logits. Yeah, that's a softmax. It's basically a simple normalizing function that can handle negative numbers. It has lots of cool properties. We won't get into them now. But yeah, after you normalize these numbers, you might get like something like, 0.01. 0.01 for cat and dog, and then I don't know, 0.6 for is, because it got a lot of logit mass, so it's going to have a very high probability. Yeah, that's it. That's what the softmax does. It's just a normalizer. And now that you know that, we can get right back into the video. That's it. That's our entire simple language model. It's got two matrices. There's the input embedding matrix that has a representation for each input word, right? So it has a representation for Ophir, a representation for Alex. That's where we took this vector from. And then once we have the input word, we multiply it by this matrix, which is, again, it's 50,000. So the input word embedding matrix is 50,000 vectors of size 1,000. The output, this is going to be called the output word embedding matrix, or forget the word embedding here. So this is just the output matrix, and that's of size 50,000 times 1,000. And that's it. So we just have two matrices in this model. And so at first, our weights are going to be randomly initialized, right? So I'll put in the word Ophir, and I'll ask the model, hey, what do you think the next word is? And it'll say, it'll give you this distribution over the next word, and it'll be totally random, totally uniform over all the words. It's going to be really bad. And we're going to use the cross-entropy loss. And so, like in this example, we know that the next word is, right? We crawled a lot of web pages on the internet. One of them said Ophir is teaching Alex. So this is what we're using as our true labels right now, right? So the input word is Ophir. The model just gives us like very uniform distribution. So it's not going to be like 0.01 or 0.02 like I showed you. It's just every word is going to receive probably 1 divided by 50,000 roughly. It's going to be totally random. And we're going to use the cross-entropy law. So that's going to push us to try and give probability. So we're only going to look at the probability that the model assigned to the correct word, which is. And we're going to push it to change that to be in 1, to move in the direction that makes this output probability 1, right? So that's one training step. And then we're going to do this billions more times or millions more times. And every time we just slightly change the weights, slightly change the weights, slightly change the weights. And at some point, it'll be a very good single word language model. So yeah, I think I said everything I wanted to say about the single word language model. Do you have any questions?
Yes. So is the that first matrix
Yes.
that creates embeddings, that'll
Exactly.
be 50,000 by 1,000,
Exactly.
and we give in these one hot vectors. Is that in practice what happens?
Yeah, so the one hot thing is just a technical thing. Basically, we have for the inputs, we have a matrix of 50,000 times 1,000, and the way I presented it is like you just choose the right. You don't even have to think of this as a matrix. You can just think of it. I mean, it's implemented as a matrix, but you can just think of it as a list of 50,000 vectors of size 1,000. It's implemented in practice. It's implemented as a matrix. So if this is the output matrix, there's another matrix which is the input matrix. And so in practice, it is a matrix of size 50,000 times 1,000. And so instead of selecting the right vector, we can just multiply it by a one hot vector, and that selects the row that represents our current input word or whatever. But that's just technical stuff. I think it's better to view this as a collection of 50,000 vectors.
Okay. But yeah, in practice, both of those matrices will be learned as part
Both of them are learned, exactly.
Okay.
Yeah.
All right, yeah.
They start out totally randomly initialized, and the model's total trash at first, and then you slowly learn.
Yeah, the reason I asked this, and we can maybe veto the question if it's like too in the weeds or something,
Yeah.
but I'm wondering because like there's no nonlinearity between the input and this O matrix.
Right now, there aren't any nonlinearities, right? That's a good observation.
Yeah, so then it's like, but it is important that we actually implement these as two matrices in a row when we're doing training, because like those two matrices, I could put them into one, I guess.
Oh, yeah, we'll talk about that later, why they have to be two different
Okay,
ones.
all right, cool.
Because later on, it's actually a paper that I wrote that I showed that you can use the same matrix for both of them, but right here you can't. Wait, another thing popped into my head now, but I forgot what I wanted to say. Okay, I think so. Yeah, so this is the most basic language model you can build. It's the word to vec model basically, but you don't have to know that. One cool observation, and we'll only briefly talk about this, is that when you do this, so you had a lot of text, you didn't have any labels, you just had a lot of text, right? You had all these sentences. Ophir is teaching Alex how to. So you had these long strings, and they were like, you made training examples from these long strings, right? So the training examples here is like, okay, when I input Ophir, I want you to output is. When I input is, I want you to output teaching. When I input teaching, I want you to output Alex. When I input Alex, I want you to output how to, right? So just millions or billions of these examples from this like from these unlabeled documents. And the cool thing that happens is that these input representations here, they learn really quickly to map similar words to similar areas in vector space. Right, so we have this really high dimensional space. I don't know how to visualize, R of 50,000, but if we're looking at R2, intuitively what happens is that the word embedding for Ophir is probably really close to the word embedding for Alex, but that's really far for the word embedding for, I don't know, car. But car is close to motorcycle, and then teaching is really far away, but it's probably really close to learning and so on. So similar words are mapped, the model learns to map similar words in the input space to similar places in vector space. And that's because similar words lead to similar outputs here, right? If I told you that the current word is Ophir, the output distribution is going to be very similar to if the current input word was Alex. And so it's beneficial for the model to map them close by in vector space, right? Because this function, I don't know if it's, this is continuous, but it should have this continuous property. Same is true for motorcycle and car, right? If I input motorcycle here, the output distribution is going to be very similar to if I input car. So the model learns that it's going to be beneficial for it to map motorcycle and car to similar places in space. In our paper that we wrote in 2017, which I'll refer to a few times, called Using the Output Embedding to Improve Language Models, we showed that the same thing also happens in the output embedding. So here, every word has a column, right? Because we're using this matrix to take this vector and transform it into probabilities for each word. So each of the words here, right? So this first word here is controlled by this first column here, and the second word here is controlled by the second column here, right? And so this vector controls how much probability dog will get at this time step. And this vector, the first column, controls how much probability cat will get. And so in the output embedding matrix, similar words are also mapped to similar positions in vector space, because if given the current word, the chance for dog is really high, I want the chance for cat to also be really high. If the chance for Alex is really low, I want the chance for a few to also be really low. So both in the input embedding matrix and in the output embedding matrix, similar words are mapped to similar places in vector space. Okay. So that was our first language model, and we're going to build 4 more in order to get to GPT-4. So this is pretty cool, and in 2013, this was the state of the art, or this was a very strong model, and people did a lot of things with it, and it was really cool. But there's a huge weakness here. Our model is only looking one word back, and that's not great. We could do better. So one thing we could do is we can build a model that takes in 2 words, right? And now it has 2 representations of size 1,000. So before we had a model that took in 1 word and predicted the next word. So let's make a model that takes 2 words and somehow transforms them into one giant vector, so these are 2 vectors of size 1,000. We can somehow transform them either to one vector of size 2,000, or we can transform them to one vector of size 1,000. And then from that, do the softmax thing again and try to predict the next word, right? So we want our input embedding and output embedding to be the same size. So let's have a, so we have these two word representations of size 1,000 and 1,000, and we want to transform them into one vector of size 1,000. So let's just have a matrix here of size 2,000 by 1,000. Right, and then we have a vector of size 1,000, and then we use a softmax thing, we get a distribution for that. But then now we have a model that can only handle 2 words. So we can design a third model that can handle 3 words, and it's going to have like, you know, a matrix of size 3,000 by 1,000 or whatever. But that can only handle 3 words. We can build a model that can handle 4 words. That can only handle 4 words. So we're going to do something a bit smarter. That can handle a whole bunch of words. And it does it in a pretty smart way. The main kind of idea is that if we had all these different models, one for handling 2 words, one for handling 3 words, you would need to constantly, like if you had 80 words, you'd need to use a different model than if you had 73 words, and like you'd need to train all these different models, and like you're using different weights. Right here we had this matrix of size 2,000 times 1,000. Here we have a matrix of size 3,000 times 1,000. It doesn't make sense. Can we build a model that can handle more words than that, and also where the number of weights in the model don't depend on the input sequence length, right? Because this model is growing, like this kind of idea that I drew down here, it's going to grow pretty quickly, right? If we wanted to handle 1,000 words, it would be like a lot of weights. We need to build an architecture that's not really dependent on sequence length, but can handle large sequences. And that's why we're going to talk about attention, because that's what attention solves. And attention is super cool. And here's how it works. So let's say we have I don't know, 5 input words. Right, and they're each of size 1,000. So one solution we could have done is to have a matrix of size. We kind of want to summarize it. We don't want this 1,000 number that I keep on saying, that's what we call the hidden dimension. We don't want our hidden dimension to keep on being dependent on our input sequence length, because then it'll just explode. It'll be too large. We won't be able to fit it in the GPU. We want our hidden dimension to stay constant. And so we can just take each one of these words and concatenate them and then have a matrix of size 5,000 times 1,000. But that's still pretty large, and it depends on our input sequence length. So we're going to invent a different way to summarize these 5 vectors into one vector. Okay? And here's how we're going to do it with attention. So the kind of idea behind attention is to just sum up all of these vectors. But to sum them up in a smart way. So I guess the kind of easiest kind of semi-attention like method is just to take your 1, 2, 3, 4, 5, 6 words and to represent them as the sum of these 6 words, the average of these 6 words, sorry. Right, so you have 6 vectors of size 1,000. Let's sum all of them up and divide it by 6. And that will be our representation. And then we take that resulting vector and we feed it through the softmax layer. We softmax it, and that's it. And then we have a language model. So this is a language model that is able to handle inputs of varying lengths. And yeah, this would work. This isn't attention quite yet, but this would definitely work. It wouldn't work as well as attention, but it would work. Attention is going to be a slightly smarter implementation of this. But questions on this semi-attention model?
So far, yeah, that makes sense to me. I mean,
Okay.
I'm very curious as to the intuition of why adding or averaging these embeddings would make sense. So that's, yeah, I guess we may get to that. But I do see that it allows for any k length.
Oh, you're like, why does it make sense to average embeddings? Yeah,
Right.
for sure. Like, that's a question that you're asking? Yeah, I mean, that's a good question. So first of all, like a lot of things in deep learning, you just try stuff out, and if it works, it works, and you use it. If it doesn't, you don't use it. So a lot of things I don't like. I'm gonna give you an answer, and because I've been training these models for a long time, I have pretty good intuition as to what works, what doesn't, and kind of why things work maybe, but like not really. Like nobody knows why any of this works. I'm going to give you like my kind of hypothesis, but it's not really an explanation. I don't really know what's going on. I think I kind of might know, but like I don't know for sure. And nobody knows for sure. Anyways, you have this really large vector space, right? And cat and dog are here, and chair and table are here, and teach and taught and learn are here. And so if you average a vector, if you get a vector and it's somewhere here, it's like, okay, this has to do with like a dog learning. Like this vector space has kind of semantic meaning. A vector's location has meaning, right? So what did I say that these words were? Chair and table. So this is chair and table. This is taught and teach. So a vector here is something that is related to a chair and a table, and also related to learning. So maybe this is like a table at a school or something. But there's definitely meaning to averaging two vectors. And also, like another hypothesis is that because every vector is 1,000 numbers, a neural network might be able to take a vector that's an average of two concepts, and kind of be able to decompose it into the two concepts that were stored inside it. Just like if I were to take an image, a digital photo, and I were to average two photos, like one of a cat and one of a dog, and I were to mix them together, right? Like I were to go in Photoshop and I do 50% of the cat and 50% of the table, and I would send it to you, you'd be able to see, okay, that's a cat in a table. So I think it's a combination of all of these things that allow for the concept of averaging 6 vectors to make sense
Okay, yeah.
for the neural network.
That makes sense. But there's no ordering being, preserved here. It's just like, look, you're talking about teaching, there's desks, and you're just like, what is the next possible word in this kind of space? Okay.
Right now, there's no ordering. There will be ordering later on, but yeah, there's no ordering. This would still work. It wouldn't be the best thing in the world, but it would definitely work. So the next step in attention, or the next step to get, so this still isn't attention. This is just like very basic, simplified, and heavily weakened attention. But the first step that we're going to have to work on, maybe this is the only thing, is to just change these weights. So right now we averaged 6 vectors, and we gave them all a weighting of a 1/6. And now we're going to make this more dynamic. The intuition here, I think, is pretty clear. If I'm trying to predict the next word in a sentence, some of the previous words are going to matter a lot, and some of them will not matter at all. For example, if I have a sentence like, I'm sitting with Alex in a blue, Alex is wearing a blue shirt, sitting next to me in New York City, and he's asking me a question about transformers, so I will tell him, and I have to predict the next word now. A lot of these words are totally irrelevant. Like, I don't care where we are, I don't care what you're wearing, but I do really care that it said, like, teaching Alex transformers or whatever, right? That's super important. So words have different importance levels. And when we're trying to predict the next word, it's really important to know how important each previous word is. And so that's what attention is going to do for us. And this is how it works. When I first read the attention paper, I think this was when I started doing deep learning research. This was 2015. I remember I printed out the original attention paper. This was Badanu et al. And it took me 2 months to figure it out. Like, it took me 2 months until the point where I was like, oh, okay, I understand what's going on here. So it's going to take you a lot of, you're going to have to listen to me explain it, and then maybe a bunch of other people, and then at some point you'll get it. So don't worry if you don't get it at first. But this is how attention works. So attention is just about, so we know that we're going to have this sum, this weighted average, and attention is about how to set the weighting for each one of these previous words. That's attention. Attention is just the method that we use to set the weighting. It's not going to be a sixth. It's going to be dynamic, and it's going to be different for each word, and attention just tells you how to set those weights. So we can set these weights in the following way. So we're doing language modeling, and let's say we're looking at 3 words. So we have 4 input words, and we're trying to predict the next word. So we're going to call our last input word, we're going to call that the query. Because that's what it's called in attention. And we're going to call all the previous words, including the current input words, we're going to call those the keys. So this is going to be key 1, key 2, key 3, and key 4. And these are all, so we have these input words and we've embedded all of them. So these are all now being represented as vectors of size 1,000. And to set the attention weights, this is a simplified version. I'll show you the real equations later. But for now, to set the attention weights, we're just going to dot product the query by all the keys. So we're going to do Q times K1. Okay? So we're going to dot product. When you dot product 2 vectors, you get a number. So, right? So let's actually put some words in this example. I sat on the. So we're trying to predict the next word, right? So the second word here is really important. All the other words probably not very important, right? So when we dot product these vectors, we're going to get numbers. So this is probably going to be equal to like 3. And this is going to be equal to like 50 maybe if we have a good model. And this is equal to like 10. And this is equal to like 2. I don't know. And then we're going to softmax these values, right? So we're going to softmax it. And I don't really know how to do mental math, but it's going to be something like 0.001, 0.98. right? Whatever. This is a 1, 5. So now we have these values, and these values, they are going to be called attention values. And our whole point here was that we wanted to produce a vector to represent this entire input sequence. We wanted to produce a vector of size 1,000 to represent this input sequence of 4 words. And here's how we just did it. To produce this vector, we're just going to multiply 0.01 times the word embedding for I plus 0.98 times the word embedding for sat, and so on and so forth. And that will result in one vector of size 1,000, which we will then apply. We will then multiply by what I called the output embedding. Do you remember this vector, this matrix from here, the output embedding? So we will then multiply that by the output embedding, resulting in a vector of size 50,000. And then we will softmax that vector, and that's it. That is our output. That's our output distribution. And now I've shown you how to take a bunch of words and build a model that can predict the next words. So this is a very basic implementation of the attention mechanism. Do you have any questions?
Yes, so this, if I understand correctly, this attention mechanism, the last word has a special, gets a special, is special basically, and because it gets a query and a key, and you're taking the dot product, with all the other words, including itself.
Correct.
And this is all for eventually for the prediction of the next word. But for now, we should just view it as a thing for taking sentences, or 4 token, 5 token, and turning these into representations. Is the way I should think about this. When you finally do the you do 0.01 times this vector, the vector for I, so you're just getting representation for these 4 words. Okay, yeah, no, I think that makes sense if I'm right there.
So in this implementation of attention, the query and key 4 are both the same vector. It's just the vector for the.
We're not learning these yet. Okay, maybe.
We are. We're learning. We're learning everything.
Oh, okay.
But right now, Q and K4 are just the embedding of the.
Okay.
And this is all learned.
Okay, that makes sense. Yeah.
And our goal here, as it's going to be throughout this entire thing, is to build a language model. The first language model that I built was kind of not great, right? It only could get in one word and output the next word. Now I've shown you how to build a language model that could handle 5 or 100 or 1,000 words. And it's a language model. But when we're doing attention, it's just for the means of taking in a bunch of words and summarizing them into one vector. Because I could have taken in all these words I set on they each have a representation of size 1,000, then concatenated it, and then had a matrix of size 4,000 times 1,000 and use that. But then if I wanted to have 100 words, that matrix would get huge. It would be 100,000 times 1,000. If I wanted to have 1,000 word inputs, it would just be impossible. So we need to build a model that is independent of input length. Because if it's not, it would just get too big. So that's what we did here now.
Now, right now, since it's all they're all the same, if the Q and the K are the same,
Yeah.
Then I am just looking for similarity of words currently. I'm looking for how similar is. So it's I
Yeah,
got
yeah.
on.
There's an issue here. This is not how you actually implement attention. So, um, let's go to part 2.1 here, where I tell you how to actually implement attention. And it's actually not that different. So the only difference, but you're right, there is an issue right now here. So the way to solve it is, so again, you have 4 input words. This guy is the query, and all of these are the keys. And so actually, when we embed these words, let's call it E1, embedding 2, embedding 3, and embedding of the 4th word. And your query, it's actually not going to be E4. It's going to be equal to this Q matrix. We call it the query matrix times E4. So the Q matrix is going to be a matrix of size of 1,000 by 1,000. Okay? And your keys, they're not just going to be E1, E2, E3, E4. They're actually going to be equal to, so K1, the first key, is going to be equal to K, a matrix called K times E1, and K2 is going to be equal to K times E2. And this K matrix is also going to be of size 1,000 by 1,000. Okay, so now that correct issue that you pointed out previously is kind of solved. So now the model is going to learn these K and Q matrices such that words that need to attend to each other will be close by in space. So it's going to during training, it's going to notice that, like, I don't know, if the current word is it's going to notice that the word sat needs to be attended to if the current word is right? Like I'm talking in like that's probably not exactly what happens, but it's going to notice that, and it's going to modify the Q and K matrices such that that will happen. Or if it notices that the word dog should never really attend to the word blue, it will notice that, and it will modify the Q and K matrices such that attention between these words will receive a lower value. So again, these matrices are initialized randomly, and through training, the model learns which words should really attend to each other in order to minimize loss, and which words should less attend to each other in order to minimize loss. Yeah, any other questions about?
No, so far so good.
Okay, great. Okay. So there might be an issue here. And that is that currently, when we're inputting these words, there isn't really any ordering being given with the words, right? In this model that I showed you here, if I were to feed an I set on and ask you what the next word is, and I were to feed in I the set on, it would be the exact same. Now with these 4 words, if I were to totally shuffle them, you could understand what I'm trying to say and what the right order is, but order really matters in language. Like if I say Ophir taught Alex, that has very different meaning than Alex taught Ophir, right? So order matters, and sometimes it's not recoverable from a shuffled state, right? If I say, yeah, if I shuffle the words Ophir taught Alex, you will not be able to recover whether the right order was Ophir taught Alex or Alex taught Ophir. And so in the original Transformer paper in 2017, they introduced this concept of position embeddings. And so what position embeddings do is they are inputted with, we have these 4 input words, and previously we said that this word was represented by embedding 1, this word was represented by embedding 2, embedding 3, and embedding 4. So what position embeddings are trained vectors which are added to each word vector before we execute the rest of the algorithm. So now we're not only telling it, hey, the first word is the, we're also telling it, and it's at position 1. Or this word is, the second word is, I don't know, dog, and it's at position 2. And so these are called absolute position embeddings. And at first, just like word embeddings, they are initialized randomly. But throughout training, they are learned. It's called learned absolute position embeddings. And the model learns a certain embedding for position 1, a certain embedding for position 2, and so on. And again, these exhibit like the properties that you think they would, where the embedding for position 1 is very close to position 2, slightly further away from position 3, but still close by. And yeah, you can use these to imbue your transformer with positional understanding. In the original transformer model, they also proposed a non-parametric position embedding. It's called sinusoidal position embeddings. So those positional embeddings are not learned. There's just like a deterministic algorithm that generates these vectors in R of 1,000 or whatever. And they generate these vectors such that the vector for 1 is very close to 2, it's kind of close to 3, further away from 4, and so on. Like similar positions receive similar vectors. So that's another thing you can do. We're not going to talk about position embeddings too much in this video because I have a lot of other lectures where I've talked about my thoughts on position embeddings, but I think that position embeddings are not the way to go because what happens is that transformers end up overfitting to specific position representations, and it makes it so that they cannot extrapolate to longer position to longer input sequences at inference time. So if they're trained on subsequences of size 1,000, they can never understand subsequences of size 1,001 during inference. And so I am against position embeddings, and what I do in my models to give them positional understanding is I used a method that I invented a few years ago called alibi. And the way alibi works is that we don't have position embeddings at all. What we do instead is in this attention computation where we have, here's where I drew it, where we have Q times K1, Q times K2, Q times K3. We just modify that. So instead of having Q times K1, Q times K2, Q times K3, and Q times K4. So if you remember, our query over there was the 4th word. So what we do in alibi is we just subtract a bias that is linearly decreasing in the distance between the query and the key. So instead of Q times K4, we would do Q times K4. Well, here it would be the same. It would be minus 0, B, bias. So this is just a float. B is just a float. And here, because it's the Q is the 4th word, we would subtract 1 bias. And again, the distance here is 2, so we would subtract 2 of these bias. And here the distance is 3, so we would subtract 4 of these bias. We make it so that attention understands the positionality of words by having this bias that grows larger as words are further away. So nearby words have an easier time attending to each other because the bias is very low. But as you grow further away, if you look 1,000 words back, they have to fight this bias. So B is a positive float, and they have to fight this bias that's gets bigger and bigger as you move farther away, and that gives transformer models position information in a way that does let them extrapolate to longer sequences at test time. Only quick questions about this because I don't want to. Positionality is a very deep subject, and I don't want to get too lost in it.
Fair. Okay. Yeah, we can leave. I guess the one quick question
Yeah.
would just be every single. You always use the same bias for every single embedding. Like there's a single constant non-negative B.
Yeah, so there are two things that I left out of my attention explanation. One is that when we do attention, we actually do multi-headed attention. I might talk about that later. And so we have different biases for different heads, but it's a technical thing. It's not really critical right now. So yeah, so that's attention and positional embeddings. I left out two technical things about attention that are just not very easy to kind of understand afterwards and not very critical. I mean, they are critical to attention working, but they're not like super deep, interesting subjects. So one of them is that I talked about the key and query matrices. There's also something called a value matrix, but it's not that important. Another thing is that when we do attention, we do it in a multi-headed fashion. So when we're doing attention between Q and K or Q and K4 or whatever, we're actually not doing attention just once. We're doing attention multiple times. So the way you can think about that is you can view every query. Let's say we're going to do two-headed attention. So take each one of your queries, each Q vector, and split it in two. And then take each one of your K vectors. So we had 4 of these K vectors. So split that in two. And then when you perform attention, do it twice. So first, multiply this half, this part of your Q, your query, by this part of Q1, Q2, Q3, and Q4. And then multiply this half of your query by this half of Q1, Q2, Q3, and Q4. So we've just performed attention twice. And then do the softmax and everything in the sum. Do that twice on halves. Or do that 3 times on thirds or 4 times on fourths. So in today's big transformer models, we actually do like 100-headed attention. And what that does is when we're kind of trying to predict the next word, sometimes like let's say I'm saying I was teaching Ophir and Alex how to build transformers in a quiet room, and then the next word I want to teach, and the thing they said was, so when I'm trying to predict the next word, I might want to first focus just on Alex, so I'll have one head that looks at Alex and the things related to that, and then I might have another head that looks at Ophir and the things related to that. So when you're doing attention likes focusing on one thing, and so you might want to focus on a few different things, and that's why multi-headed attention is really useful. You might want to have one head just focusing on people, one head focusing on what environment are we in, one head just focusing on, I don't know, colors. I don't know. Like you have a lot of heads, because if you only had one head, you could only focus on one thing at a time. But a lot of times when we try to predict the next word, we need to kind of figure out a few different things about where we are, what we're trying to do. And so that's why having multiple heads, each focusing on one thing, is really good. So that's multi-headed attention. Okay. So let's review the model that we have right now. We've got a bunch of words. So I've been showing this on 4 words, but this model can handle 100 words, 1,000 words, right? We have 1,000 words, or 100 words, or 50 words, whatever. And we did attention, and we summarized it all into this one summary vector. And then we multiplied it by that big, so this is a vector of size 1,000. These are all vectors of size 1,000, right? We summarize them into one vector of size 1,000. We multiplied them by the very big output embedding matrix. We got a vector of size 50,000. We softmax that vector. And now we have a distribution over the next word. Now we have a working language model. And of course, we're feeding it, right? So what we do, so let's say we decide on an input length for this model. Let's say it's 100. So that means that we're sampling sequences of 100 words from the internet, or sorry, 101 words from the internet. We sample a sequence, we feed in 100 words here, and then we know what the correct next word is. That's our 101st word. And then we use a cross-entropy loss. We backprop, we get gradient updates, we update, and then we do it again and again and again, each time with a different sample of 101 words from the internet. This vector, so again, this is a lot of my intuition. This is my kind of explanation for why we do the things that we do. It's just intuition, right? But here's my intuition. So the next thing that we're going to add, this is going to be our third language model. We're going to add a feed-forward layer. So what we have here is basically a summary vector of all of our inputs. But we're trying to predict the next word. We're not trying to summarize, we're trying to predict. And I think when we're trying to predict, it would be really useful if we could sneak something right into here that could take the summary vector and say, okay, based on this summary of what's going on, this is what I think will happen. Based on this summary, this is what I think will happen. Kind of a mapping network that's like, okay, based on this, this is what should happen. Based on that, this is what should happen. Okay, there's a dog and something about learning and a table, this is what. Okay, there's a tree and something about a park and something about a bike, this is what should happen. And so the mechanism that's going to do that is just a simple feed-forward network. It's just a very basic neural network. And yeah, it's just a network that takes in, so we have a representation of size 1,000, so it takes that in, it multiplies it by a matrix of size 1,000 times 3,000, and so now we have a vector of size 3,000. It applies some non-linearity, okay, and then it multiplies that by a matrix of size 3,000 times 1,000, resulting in an output of size 1,000, and that is called the feed-forward layer in transformers. Yeah, and that kind of, my intuition for what's going on over there is that let's first draw how this network looks, how our current language model looks, and then I'll give intuition. So we have our 100 input words, or 1,000, or whatever, a set number. And then we use attention to take all these words and output one vector of size 1,000, and then we feed it to this feed forward layer, which I just showed you, and then we multiply it by the output embedding. We get a vector of size 50,000, and then we have the softmax, and it's still 50,000, and that's our output. So that's our current model. And my intuition is that the attention model is responsible for figuring out what our input looks like, figuring out what we're dealing with, and then the feed forward layer is kind of the brains behind the operation. That's like, okay, if this is what we have now, this is what I think the next word is. If this is what we have now, this is what. Yeah, that's it. That's our third language model. Questions about the feed forward layer? So, of course, again, the feed forward layer starts out like these two matrices start at randomly initialized, and then you learn them through training.
Yeah, I got some questions. Is it typical that this this feed forward thing back here? I noticed that the dimension increased from 1,000 to 3,000.
Yeah.
We typically
the norm. That's what they do. Yeah.
Okay.
And then just like everything in deep learning, there's no like, it's not like physics where like it must be 3x or the plane doesn't fly. People explored a bunch of different things, and I guess this kind of worked well. The nonlinearity that transformers first started with is not the same one that people use today. I think people are using like Swigglue or some crazy thing now. So like everything in a transformer is it's possible to improve anything, and nothing is set in stone. And these things were all discovered through empirical experimentation. They work. There's probably other things that work, some of which might work even better than what we have now, and we're trying to discover them.
Okay, and then I had another question from before that we can veto, because it is about some the multi-head thing.
Yeah.
Which was that when you do the multi-head thing, does that mean that you're going to actually have a bunch of distributions that you then have to somehow combine?
Exactly, yeah.
And so how do you do that?
You have one distribution for these keys and one distribution for these keys, and then you sum the first halves according to the first distribution, the second halves according to the second distribution.
Okay.
Other questions about the feed forward layer?
I think no.
Okay. Yeah, this is already a pretty strong model. But one thing that we've discovered in deep learning is that deeper networks are better. And so what we're going to do is we're just going to make this network deeper. So we have our 100 or so input words, and then we have an attention layer, and then we have a feed forward layer. And we're going to have more and more of these layers. So if you have a feed forward layer, if you have an attention layer followed by a feed forward layer, that's called a transformer layer. And so what I just drew is a 4-layer transformer language model. And then after those 4 layers, we continue just like we did before. So we have an output here of size 1,000 at this time step. And then we multiply it by the output embedding. We multiply that by the output embedding, we get a vector of size 50,000. We softmax that, and then we have our output. The only thing I need to explain is what are we attending to here, and what are we attending to here and here. So let's draw this out time step by time step. So the first time step, so let's say we have 100 input to, let's say we have a language model that works on 100 words. So what actually happens, in order to make training efficient, right? So we're building a language model that can handle 100 words, but we're not going to do what I was saying before of having like 100 inputs and then trying to predict the next word, and then we'll move on to the next 100 inputs, try to predict the next word, and so on. No. What we're going to do is we're going to have this sequence of size 100, and at every time step, we're going to try and predict the next word given all the words we've seen up to now, right? So if the input sequence is, if the input sequence here is I sat on the tree, what we're going to do in the first time step, we're going to input the word I, and we're going to try and predict the word sat. In the second time step, we have access to I and sat, and we're going to try and predict the word on. And in the third time step, I said on, and we're going to try to predict the word the, and so on. So the kind of official name for this is, for what I'm about to explain, is causal masking. And so when we're training a language model, we're actually we have 100 input words, we're actually making 100 predictions so that we can learn as much as we can from this singular input. And here's how it looks. So I input in the first word. So we have a 4-layer transformer with 100-word input word. So I input in the first word, and then I have to do my attention layer. So it's just going to, this happens, but this attention layer is going to have to attend to one input, which is the key in the query, and it's going to assign 100% of its attention to this one input because that's the only option. And it does this very, silly attention layering, or attention, and it has an output, size 1,000, and then we do the feed-forward network, and then we take the output of the feed-forward network, and now it's our second transformer layer. Again, we attend just to this word, and we have some kind of output, and then again we do the feed-forward, and so on and so forth, right? So the first layer, the first time step in this 4-layer transformer is very simple. Now, it's time for the second time step. So we embed the second word, and now in our attention layer here, we can actually start doing real attention for the first time. So we're going to attend to these 2 words, and we're going to have some kind of distribution. We're going to produce an output, and it's going to be here. And then we're going to pass it through the feed-forward layer here. And then again, in this layer, we're going to attend to both of these words, and we're going to have an output and then feed forward, and then again attention here to both of those words. And so on and so forth until we get to the top layer. And then third time step, again, we input a word. Now we attend to all 3 previous words. We have an output, feed forward, blah, blah, blah. So attention at every time step is attending to words at the same layer, right? Here, we're going to be attending to these representations. Yeah, and that's a really cool thing about attention. It's constantly contextualizing the current input word based on contextualizations of the previous words. And at every layer, it's getting better and better at understanding what contexts it has to pull from the previous words. And the previous word representations themselves are getting better and better because they've been through so many of the feed-forward layers. They've contextualized themselves many times. But yeah, I view attention as a kind of contextualization layer. Like in the lowest layers, you just have words. And you might just have the word Alex. But then in the higher layers, I'm adding more and more to the representation of Alex. Like maybe I know that he's wearing a red shirt. Let's add that into his representation. Maybe I know that he's sitting down. Let's add that. We're contextualizing. And so these, as we go deeper into the network, our representations become better and better and more enriched. Yeah, so I think this is the fourth. So our third language model was just one attention layer and one feed-forward layer. This, you can train this. It will work. It won't be very good, but it will definitely work. And our fourth language model is stacking multiple transformer layers one after the other. And now we have a very strong language model, especially if we have like enough of a hidden dimension, if we have enough training data, if we have enough transformer layers stacked. That's it. That's a pretty strong language model. So we're mostly done. There's just a few small things I want to go over. But this is basically GPT-3 or ChatGPT. Well, actually, we don't really know what's in ChatGPT, but this is basically GPT-3. GPT-4 is probably a mixture of experts model, which isn't so much more complicated, but I'm not going to talk about that now. But yeah, this is GPT-3 or Llama. This is basically it. There's a few small things I want to elaborate on. So, in all of our models, we've had the input embedding layer, right, which produces these representations down here. And then we've had the output embedding layer. And early on, I told you that for these representations, it's pretty clear why similar words receive similar embeddings, right? Because given a similar word, we know that the output is going to be similar. So it makes sense to give the word blue and the word green similar embeddings. It makes sense to give the word table and chair similar input embeddings because if we had a sentence and we changed the word blue to the word green, yes, the output distribution will change, but not by a lot, right? Not by as much as if I changed the word blue to the word bicycle. So input words receive similar input embeddings. And the same thing is true in the output embedding, right? The output embedding is the thing that takes the output of the last transformer layer and tries to decide how much probability to assign to each word. If I know that I'm assigning a very high probability to the word bicycle, I should probably also assign a very high probability to the word bike. And so in the output embedding, output words control the probabilities that each word gets. And so if we want to have that happen, which is something the transformer model wants to do, output words also receive similar representations in the output embedding. And so in 2017, we wrote a paper where we showed that so everybody knew that the kind of the input embedding leads to similar words having similar representations. We showed that the output embedding has the exact same thing, and we showed that in the language models of the time, which were not using transformer layers, they were using LSTM layers. But we showed that at the time, the output embedding resulted in similar representations being learned for similar words, and these representations in the output embedding were actually of higher quality than the ones in the input embedding. And so we propose just using the same matrix in both places. It's called weight tying. You can only do it if you have these non-linear layers between your output embedding and input embedding. So you couldn't do it in the first model that I showed, the 2013 model, but you can in all the other models. And yeah, it's called weight tying, and a lot of models use it. So I think BERT used it. I think like GPT-2 used it. A lot of models use it. Llama doesn't use it, but other than Llama, like a lot of models use that thing. It used to be a huge like resource saver and parameter saver. Now these parameters are really small compared to the rest of the model, so it's not as important to do it, but it's just something cool to know. The other thing I wanted to talk about is that I didn't talk about layer norm, and I won't talk about layer norm because it's just a boring technical thing. But yeah, you should know that there's like layer norm layers distributed throughout the transformer stack. Another thing I wanted to mention is residual connections. So those are really important and really easy to explain. So what I showed you before is that we have, at each time step, we have an embedding. Which gets fed into an attention layer, which gets fed into a feed forward, gets an attention, feed forward, blah, 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 right? But that's not what actually happens. What actually happens is that at every time the output from each layer is actually the input to that layer plus the output from that layer. So the output here is actually the whatever the computation here was plus the input. How do I draw this? Here's how to draw this. So this is our input. And this is the attention, let's say. And we're going to add both of these things, and that's going to be our output. And then if this is the feed forward layer, the output here is going to be added to the output from the feed forward layer. So that's a residual connection, and it's very important, and it happens at every layer in a transformer network. Yeah, it's basically critical for the thing to work. So yeah, I'm not going to get into that because there's a lot of content about that online. And the kind of last thing I'll say is BPE. I'm not going to get into that because that's also, there's a lot about that online, but when you train a language model, the vocabulary that you pick is really important, right? So you could do language modeling at the character level. Like, let's feed in a character, one character at a time, and try to predict one character at a time. You could also, if you really wanted to, you could make a sentence level language model. Just have a list of like, a million different sentences, and that's how your language model works. It can only take in one of these a million sentences and predict a next sentence. That would be kind of silly, but you could do that, right? So vocabulary really matters. And for a long time, a lot of people in NLP were spending a lot of time understanding what the best vocabulary, and I mean, people still do that. And what we've settled on is BP, but that doesn't mean that that's the best thing, and that doesn't mean that we won't have somebody coming in a year and showing us how to do it better. But most transformer models today, or most language models today, use something called BPE, which is this, it's called a subword vocabulary. So what BPE does is any word that's really, really popular is going to be fully within the BPE vocabulary. But any word that's less popular is going to be broken down into subwords, or any word that's long is going to be broken down into subwords. So the word Alex is in it's probably in the GPT-4 vocabulary or whatever. But if you have Ophir, that might be very rare, and that might be broken down into characters, like O, and then F, and then I, and then R. Or if you have a really long word with like non-negotiable, I don't know, right? It would be broken down into non, and then negotiable. So that's BP. I won't get into that because there's a lot of stuff on this online. But yeah, that's it. We've basically built Llama or GPT 3, and we're almost all the way to building GPT-4. The only other thing we need is mixture of experts. But basically, yeah, the what we've talked about in this chapter is taking those multiple transformer stacks and then adding all of these technical bells and whistles that make the transformer language what it is. So those bells and whistles were layer norm across the network, residual connections across the network, using a BPE vocabulary and not a vocabulary of words. Sometimes people use weight tying. Mixture of experts we're not going to talk about. Yeah, that's it. Final questions?
Yeah, I was wondering if you could talk a bit about some terms that I hear now that I'm hanging around the NLP community. People,
Yes.
I think it probably connects to this residual stream. People use that term.
Yeah,
sometimes.
that's just this residual connection thing, and thinking about how when you're not using residual connections, every layer has an input and then an output, and an input and an output, and nothing from the past matters because I had an input and now I have an output. Nothing from the past matters. But when you're doing residual connections, you're adding to the residual stream. You have this kind of river, right? You have some input here, and then you're adding to it, but it still matters. And then you had another thing that you did here, but you're adding it to what you had before. So now it's kind of, I shouldn't say this word, but it's kind of not Markovian anymore. Like everything matters. Like, because here, right, when we had this input, we didn't care what the hell happened here when we're outputting this. But now I'm inputting something to a layer, but then my output from that layer is whatever that layer outputted plus everything else I had before. So I'm constantly adding to this stream, and it makes training easier, I think. Learning without residual connections is really hard for the network. And it also, it means that every layer isn't, I mean, this is really deep stuff that we don't really understand, but every layer isn't really outputting like a full representation. It's just kind of outputting a diff of this was my representation before. How am I going to change it now for the next input?
Nice. Okay, that makes sense. Yeah. So the residual stream is kind of this vector that's getting pushed forward through these layers, and it's changing as you keep adding the divs to it.
Yeah,
Okay.
exactly.
The other question is, I've heard that there is a sense in which this is like very parallelizable, even on like, is it true that even on one sentence, when you break it up, like, I guess there's a sense in which you can kind of reuse the representations for like, so is it true that like, I guess when I run I am sitting,
Right.
like, is there a sense in which I can parallelize the training for I to am and I am to sitting? Or?
Oh, yeah. So this all happens in parallel. It's kind of technical, so I didn't talk about it a lot. But when when I was discussing this, do you remember this part? When I was talking about how we had one word and we encoded it, and then we encoded the second word, and then we're encoding the third word, and then we're encoding the fourth word, right? The kind of magical thing is that when I was explaining it to you, first I encoded the whole first word, and then the second word, and the third word, and fourth word. In reality, during transformer training, if we're training on 100 words, we're actually running this whole process in parallel. So we're first encoding all of the input words in the first layer, and then we're running all of this, and then all of this, and then all of this, and so on. So we process every row in parallel, and that's one of the things that makes transformers really fast. It's called causal masking. Yeah, that's what allows us to run these things in parallel.
All right. And then one, I think, final question I had is another just definition question I hear people talk about.
Yeah.
Sometimes I hear bigram statistics as a, is that the first, like, I get this sense, is that the first thing you talk, have you heard that term?
Yeah. So I'm going to be off by one of this, but a unigram language model is, I think, a language model that only looks one word back. I think that's the first thing I showed, or that might, and then a bigram only looks at 2 words. So I don't know if that first model that I showed, it's either like a unigram language or a bigram. I always get those confused, but yeah, those are, in the past, you used to have a language model that would only look 1 word back, a different one that would only look 2 words back, a different one that would only look 3 words back, and so forth. And you would kind of combine all of these to make like a big language model. But I don't really speak that language.
Okay. But it is a sense in which just how many words back you're using.
Yep.
Yeah, that's the key. Okay, cool. Awesome. Well, thank you so much.
Thank you so much.